Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Michael Strauss, who is the chair of the Department of Astrophysical Sciences at Princeton University. He uses large-scale imaging and spectroscopic surveys of the sky to map the universe, with a particular focus on studying the large-scale distribution of galaxies to address questions in cosmology and galaxy properties and evolution. He is also particularly interested in quasars, powered by supermassive black holes in the centers of galaxies. Welcome, Michael.
I'm very happy to be here. Thank you so much.
Yeah, thanks for doing this. So I want to start with one of the papers, a little bit older papers, talking about cosmological parameters from SDSS and WMAP. So you say we measure cosmological parameters using the three-dimensional power spectrum from over 200,000 galaxies in the Slow and Digital Sky Survey, SDSS, in combination with the Wilkinson Microwave Anisotropy Probe, WMAP, and other data. So SDSS is something from the ground, and WMAP is something from above, I guess.
Right? That is correct. That is correct.
And both of these have produced a lot of data. SDSS started sometime in 2000.
2000, that's right.
Yeah, had a long tenure of 20 years with the multiple upgrades to it. And the WMAP sort of overlapped with it between 2000 and 2010 or so before Planck satellite kicked in right after that, right? So
yes, that's right.
So we have two sets of data, and really kind of combining these two data and looking at some of the theories that are being more accepted nowadays. So I want to talk a bit about the type of data that we got and what hypotheses we could create from that.
Okay, so perhaps I can just say in general terms what the scientific program there is, and what are just try to explain how WMAP and SDSS are connected.
Yeah.
So what SDSS, let's start with SDSS. So what SDSS was designed to do and did was to measure the distances, and therefore, well, to measure what are called redshifts, which is a shift in the spectrum of a galaxy caused by the expansion of the universe. By measuring these shifts, which is straightforward, if you can measure the spectrum of the galaxy, you can determine how far away that galaxy is. And so one needs to remember that when one looks at an astronomical image or looks at the sky in general, you're seeing everything as it appears in two dimensions. It's all in projection, and and if you see a star or a galaxy or anything, an asteroid, you don't know at first glance which is relatively nearby and which is far away. So to get that third dimension, one needs to measure the redshifts. And what the Sloan Digital Sky Survey was do that on a larger scale than really had ever been done before. At the time we wrote that paper, it was 200,000 galaxies. That number has now is several million galaxies. And
this is Michael. This is optical data,
yes,
right?
this is visible light, a light that your and I and my eyes can see. Although, of course, with a large telescope, you're going much fainter than our eyes would be sensitive to. So the distribution of galaxies is they're not just randomly sprinkled out there. They form in a large structures we refer to clusters of galaxies, in which several thousand galaxies may be all together in a relatively small volume of space. Large filaments of galaxies, enormous empty regions which we call voids, which indeed have almost no galaxies in them at all. And as astronomers first became aware of the fact that the galaxy distribution was so rich, that there's so much structure, the obvious question is, why is that? What's the physical process that's going on?
So the higher the redshift, the further away the galaxy is.
That is correct.
And what we mean by redshift is that the light, the wavelength of the light has shifted to a longer wavelength.
That is exactly right. Okay. So when you measure the spectrum, which is the intensity of the light coming from a galaxy as a function of wavelength, you see that spectrum has different features, which turn out to be, in the context of what we're talking about, is usually due to absorption by specific elements in the atmospheres of the stars that make up that galaxy. And those features are shifted to longer wavelengths, just as you said, by the expansion of the universe. And it's not necessarily a subtle effect. Galaxies can have their, you say if a galaxy has a redshift of 1, that means it's been shifted by 100% relative to what it would be if there was no expansion of the universe. That is, and so this is something that we can indeed measure directly, and it, again, just as you said, gives a direct measurement of how far away that galaxy is.
So will they look different optically?
Do the galaxies at high redshift, for example, look different from the galaxies at lower redshift? So in that context, what you're let me just rephrase that question. You're asking the question. So let's back up slightly. Remember that if it's a very distant galaxy, I said redshift of 1, for example, such a galaxy is that that light has been traveling to us for about 7 billion years. It's not quite the same thing as saying that the galaxy is 7 billion light years away, but because of the finite speed of light, we're seeing that galaxy not as it is today, but as it was in the past. And so another way to ask your question is, have galaxies changed in their properties through cosmic time? And of course, the context of that is remembering that the universe is only, I put that in big air quotes, only 14 billion years old since the time of the Big Bang, which means that at redshift 1, we're looking back to roughly half the current age of the universe. So, you might well imagine galaxies must have gotten started somehow, and they presumably have evolved and changed over billions of years. So the typical galaxy you might see at redshift 1, when the universe is half of its present age, will be different than a galaxy we see today.
So SDSS sort of provides a 3-dimensional view, because using redshift, you can determine where they might be, right? So I've seen some sort of movies, 3-dimensional movies. Is that based on the SDSS data?
I don't know exactly which movies you've seen, so I can't exactly comment. But yes, there are movies out there that you might have seen that indeed are based on the data, which sort of fly-throughs of the distribution of galaxies, and you can see those clusters and those filaments and voids that I was making reference to before.
Okay. So, and now the WMAP data, how is that different?
So in a sense, what we learn about from the galaxy data is the distribution of galaxies today, and then going back somewhat in cosmic history. WMAP is measuring a different phase in the universe's evolution. And in particular, the universe started in a hot Big Bang, roughly 14 billion years ago, and has been expanding ever since. It was hot, and one of the things that hot things do in general in physics, anything that's hot glows, gives off light. And so if the early universe was hot, as people had hypothesized, then all that heat there should be some radiation, some light emitted from that, and that was discovered. That concept was confirmed dramatically in 1965 by a serendipitous discovery by Arno Penzias and Robert Wilson of what we now call the cosmic microwave background, cosmic background radiation. So that is light, as it were, left over from the Big Bang. Is a poetic way of saying it. What WMAP stands for Wilkinson Microwave Anisotropy Probe. So microwave is the same microwave that I was talking about, the cosmic microwave background. Anisotropy is trying to measure whether there's any structure whatsoever I'm going to use the abbreviation CMB, cosmic microwave background. You can ask the question, the present day universe is very structured. We see these clusters and these filaments in the voids, which stretch over distances of millions or tens of millions of light years. While when you measure the cosmic microwave background, you see it's incredibly smooth. And so one of the fundamental questions becomes, and again, that is what you were seeing there is, crudely speaking, the leftover light from the Big Bang. It is a measure of what the universe looked like, as it were. It turns out, when you go through the details, you're measuring at a time about 400,000 years after the Big Bang. We could go into digression where that comes from, but in any case, you're seeing the light from 400,000 years after the Big Bang, and the present day is 14 billion years later. It's quite a bit later. So the universe seemed to have been incredibly smooth back then, and yet it's very structured today. And so one of the fundamental questions becomes, how do we get from there to here, or from then to now, I guess is a better way to say it. And so our present understanding of that is that imagine you have a region of space where it's slightly more dense, a little bit more mass is associated with this region of space than any other. Because it has a bit more mass, it has a bit more gravitational pull, and material meaning gas, we haven't made any stars yet, or galaxies might start falling towards that, and therefore increase the density a little bit more. And that
So WMAP created that CMB. I know that. So the Planck data since then just improved that.
That's right. Yes. So just to finish the logical thread, we infer from the fact that the universe is very structured today that there must have been some structure at a very subtle level in the cosmic microwave background, and that's what WMAP is measured. The microwave anisotropy probe. The anisotropy means the deviations from perfect smoothness, which WMAP measured quite well. And as you said, the Planck satellite from the European Space Agency just did that much better.
And it's really, really small, right? The differentials, like a few microkelvins.
It's a difference of 1 part in 100,000. So yes, the effective temperature of the cosmic microwave background is 2.7 degrees Kelvin, and the typical fluctuations are 1 part in 100,000 of that. Yeah, so you're right. It becomes microkelvin. If tens of microkelvin is what's being measured. But the amazing story is, and that comes back to the paper that you quoted, is that you can put together the measurements of the fluctuation seen in the early universe from the cosmic microwave background and the measurements of the structure from the galaxy distribution today, and try to put together a single coherent picture about how the one might have evolved into the other. One does this statistically with things like the power spectrum, which is some jargon we could go into, but we now have a fairly complete understanding of what the universe was like 400,000 years after the Big Bang, and how it formed into the structures we see today. And that was really the point of the paper. But let me just sorry, once you get me started, I don't shut up here. In order to make that connection, there are some free parameters that you need to know about, and those parameters end up being quantities like just how much dark matter is there in the universe, how much dark energy, which we may find ourselves coming back to talk about, is there in the universe, what is the expansion rate of the universe? There's about 5 or 6 such numbers. Some of them are a little bit more technical than those as well. And those, you need to include those to get a full picture. And but the amazing story is that it really does fit together. With 5 or 6 numbers, we can actually describe in a statistical way both what's seen in WMAP and what's seen in SDSS to really exquisite precision.
So the accepted theory today is lambda CDM, and so in the paper, the parameters, sort of the fundamental parameters like Hubble constant and so on. So we got all of that by SDSS and WMAP, and when the Planck data came in, did those things get just refined, or?
Yes. The first answer is yes. Of course, people looked very, very carefully to see. One of the questions is, I just told the story that there's this beautiful concordance, as it were, between what one sees in the cosmic microwave background and in the large-scale distribution of galaxies. And, at first, scientists are always delighted when they have a simple picture that describes everything. And they work on that, and the error bars get smaller and smaller, and they measure things ever better, and everyone's happy. And at a certain point, people say, this is fun, but it sure would be interesting to find something new. And part of the motivation for finding something new is I've already made reference to dark matter. I've already made reference to dark energy. Those are labels that we give to concepts that are required in the equations, and we can talk about each of those in turn. But if you really want to ask the question, what are these things physically? You'd like to have more than, gee, it all fits together beautifully, which is not yet a full explanation to, okay, what is the dark matter made of? What is this dark energy thing that you're talking about? And so astronomers have been very eager to find chinks in the armor, to find flaws in the logic, or disconnects where things don't fit together, because that could be pointing towards something fundamentally new. And we're never satisfied. We're never satisfied. Oh, we have a model where we know how much dark energy there is and how much dark matter is, and it all fits together, and we're all happy. But then there's still basic unanswered questions that the way to address them might be to find some aspects in which things don't quite fit together. Yeah.
Right. So the little I understand about this, Michael, so there is a general consensus that the overall proportions, about 70% dark energy, 25% dark matter, and 5% matter that we can see. There's a general consensus around that, but we really don't know what we mean by dark energy.
That is right. Well, dark matter we understand better than dark energy, and I can expand on that statement. But no, we don't. The basic question of what either of those things actually are, we do not have an answer to that yet.
Yeah, let's talk about dark matter a bit, because I know that is one of the objectives of LSST that we will talk about next. And so maybe it's good to set the context around dark matter. I know that there are a lot of candidates. WIMPs, neutrinos, primordial black holes, and so on. And so what is our sort of current expectation of what that looks like?
Well, one such candidate, sort of everyone's favorite, is that in the early universe, our modern understanding of the hot Big Bang is that various particles were created out of the very hot. Using our understanding of physics, we understand that with high enough temperatures, one can make all kinds of particles, and that's where the protons and neutrons and electrons and neutrinos and everything else came from. And maybe there was something else, which is a hypothetical new particle that makes up the dark matter. And when one goes through those ideas and tries to imagine what that hypothetical particle might be, there's one particularly strong theoretical candidate that comes out that's called a WIMP, a weakly interacting massive particle, which is it's a clever acronym, but its name describes what it is. Weakly interacting is a technical term about the kind of interactions it has with itself and with other particles. But if dark matter is made of WIMPs, we should there should be WIMPs in our streaming through us right now, because there's sort of dark matter everywhere, and it's weakly interacting, which means that it interacts at least a little bit. And so, based on that hope, people have developed. This is not my work at all. People have developed very sophisticated laboratory experiments to try to detect this stuff, and have done. They've become, in a sense, victims of their own success, which is to say that the sensitivities of these are getting so great that the WIMP, and they haven't found anything yet, that the WIMP model is starting to look like it may not work after all. And people are getting a little nervous about that, because that was sort of our cleanest and best story of what the dark matter might be made of. And it's not working at the moment, which is really, really sort of exciting and a little scary. It says that we're barking under some sort of wrong tree.
Yeah, as an engineer, Michael, and I left engineering a long time ago, but my intuition would have been the theory is wrong.
And of course, the theorists are infinitely creative and are constantly coming up with new ideas. There's a whole story why the WIMPs are particularly compelling. But again, if it doesn't agree with what's experimentally seen, then it becomes, of course, quite a bit less compelling.
And the other candidate is neutrinos, right? And the masses of neutrinos. And there's something else that came out of SDSS and WMAP data.
So physicists have long, when people first realized that neutrinos existed, the simplest hypothesis was that there was no mass associated with these at all. They traveled at the speed of light, just like photons, particles of light. But as people thought about it further, they realized there's no a priori reason that they have to be massless. Maybe they do have some mass, and again, they should be created in enormous numbers in the Big Bang, and then you try to ask whether they there might be enough of them to explain the dark matter. And to make a long story short, neutrinos don't work for two reasons. First of all, we now know we do know now with confidence that neutrinos have mass. We don't know how much it is, but we know it's very small. And with those limits on what the mass might be, and the numbers, we have a pretty good estimate of how many neutrinos there should be. There's simply not enough to make up the dark matter. That's the simplest way to explain why neutrinos end up not working after all. That's another disappointment in this regard.
The other fundamental parameter is the Hubble Hubble constant, and you got fair amount of precision around that out of SDSS and WMAP, and then I understand that there was another measurement from the supernovae that seemed to sort of disagree with
so
that.
This is very much sort of, I was saying earlier that there's great excitement, or there's great eagerness in the scientific community to find chinks in the armor, to find discrepancies, and what you're referring to is exactly that. So as your listeners may know, the Hubble constant measures the expansion rate of the universe, and there's a whole variety of different ways to do this, and astronomers have been trying to do this since the time of Hubble himself back in the 1930s. And now the measurements have gotten astonishingly precise. And one way it's the expansion rate of the universe. It's a measure of how fast a galaxy is moving away relative to its distance. So that sounds straightforward. You measure the distance, you measure how fast it's moving away from the redshift, you're done. So that's one approach. And many different variants on that particular theme, but crudely speaking, the number that comes out in funny astronomer units is about 72 or 73. When the other way to do it is to measure the detailed fluctuations in the cosmic microwave background from first WMAP, and now you mentioned the Planck satellite, which has made more precise measurements, and that gives you slightly more indirectly a measure of the expansion rate of the universe. And when you go through that in the same funny units, the number comes out to be 67. So 67 versus 73-ish, and then everyone just starts arguing. And so is someone made a mistake somewhere? Is there a systematic error? What happens if we use this other measurement that gets us 71 instead of 73? At the moment, it looks like a real discrepancy, which has gotten people all excited again, because it says, this is, we were getting a little bored by just how beautifully everything was fitting together. We need something new to give us a new handle on something. We really want to discover something fundamentally new rather than just see it all fit beautifully together.
Yeah, a couple of weeks ago, Michael, somebody else said, it used to be
That's
50
right.
and 100. We used
Right,
to
right,
take an
75.
average, 75 sort of worked. Now we are really worried about 67 and 73. It's good enough for government work.
Yeah, no, the history, when I was a graduate student, I'm now old enough, I can say that when I was a graduate student, indeed, it was the 50 versus 100 were the values over which people battled, but with enormous uncertainties. And now these two quite different ways of measuring it are getting what seem to be statistically significant differences. And again, whether, so of course, again, the theorists are having a field day and inventing all kinds of interesting mechanisms by which you could get this discrepancy, new kinds of physics that might possibly explain it.
Right. So that brings us to a new toy that's being built. The Large Synoptic
So I have to
Survey
stop you right
Telescope.
there and say
So
that it has changed its name. The paper I gave you was just published just before the name change. So by congressional decree, it was actually the U.S. Congress, this was renamed to the Vera C. Rubin Observatory Legacy Survey of Space and Time. Because Large Synoptic Survey Telescope, no one knew what synoptic meant. And anyway, there's a variety of problems with that old title. But so Vera C. Rubin, as you probably know, she was a groundbreaking astronomer, just passed away 5 years ago, something like that, who did many wonderful things in astronomy. But one of them is that she looked at the rotation, what's called the rotation curves of galaxies, the way galaxies rotate, and came up with the most solid evidence to date that galaxies are dominated by dark matter. The most of the mass of a galaxy is in the form of dark matter, and so this observatory. Yep.
This is something.
Yeah,
it's
being built in Chile. Frustratingly, like so many other aspects of our lives, the construction is actually temporarily halted because of COVID-19. But things are improving. The health situation in Chile is improving. I just heard, and things should start up again soon.
So I don't know the geography, Michael. I know there are other things. There are other things being built in Chile.
Yes,
like the
right. Further north. Yeah. So Chile is well, first of all, one of the most beautiful countries in the world. Is one of my favorite places to go. It's completely a north-south country. It's a very, very long and skinny country. And I say 2,000. Can't remember if it's 2,000 kilometers or 2,000 miles long. I should know that. But on the western side, of course, is the Pacific Ocean. The eastern side is defined by the Andes Mountains, and the northern parts of Chile are dry. Extraordinarily dry, the northern parts of the Atacama Desert, where you mentioned the Simons Observatory, for example. So that combination of mountains close to ocean and very, very dry conditions makes it really one of the best places in the world to do astronomy. And so many of the next generation current and next generation large facilities, telescopic facilities, are being built in Chile.
And the southern hemisphere also is advanced.
So when you're an astronomer and you're working from the Earth, as your question hints, you can't see the entire sky. There's parts of the sky that are hidden beneath your feet, and will be no matter how the Earth turns. So when LSST, the Rubin Observatory, when we were first having the discussions of where to build it, that was one of the questions. Would it be more appropriate in the northern hemisphere or the southern hemisphere? And after much discussion, we decided that what we need to do is find the best site in terms of its weather, how many clear nights it has, and other such things. And that was more important than agonizing over whether the northern half of the sky or the southern half of the sky was more fundamentally interesting. You can make strong arguments in both directions. Yes,
and this is an
yes.
optical
telescope. So what
it
will do, it takes pictures. That's all it does. It takes pictures. It does. We were talking about spectra before. That's not something that the Rubin Observatory will do. But what it will do is it will be a particularly large telescope. So when people talk about the size of a telescope, the things they care about are the collecting area, how large the mirror, the primary mirror is, and that mirror is about 8.5 meters across. 8.4 meters, I think, is the official number. And the other aspect of it is that you want to be able to take a picture of a large swath of sky at once, what's called the field of view of the telescope. And LSST, the Rubin Observatory, will have the largest combination of primary mirror size and field of view of any telescope in the world by a large factor. So it's particularly well suited for the mapping exercise of just taking pictures of everything that's there. The large size of the primary mirror means it's tremendously sensitive to very faint objects. Large field of view means you get a lot of objects at once.
Right. Yeah, this is a big engineering challenge, obviously. 8.4 meters in diameter of the primary mirror, and a camera with 3.2 gigapixel. And so the project started.
Oh goodness!
10 years ago.
I first heard of the first inklings of the project that I heard of was the late 1990s. Tony Tyson, who was at the time at Bell Labs here in New Jersey, he's now at UC. University of California, Davis, was starting to think about this, but it really started taking off, becoming a serious project in the 2000s, and it was formally approved by the National Science Foundation, saying yes, we're going to put money into this in 2014. So,
and it's also. So if you could describe a little bit, sort of the operations. I understand.
Oh yes. So as you said, 3.2 gigapixels, which means that every time you take a picture, which we will do every 30 seconds for 10 years straight, or at least when the sun is down for 10 years straight, we will have a picture with 3.2 gigapixels. That's covering an area. I should remember these numbers. Approaching 40 times the area of the full moon. And if I did the arithmetic in my head correctly, and so what one can do with that is you can take pictures of the sky, and we all love looking at astronomical pictures, but we can take pictures of the sky, and then we can do it again, and then we can do it again, and we do it again. So why do you keep on doing it? I say, I've got a picture. What more do you do? Well, the first thing that you do is you add those pictures together, and so you get an effective exposure time. That will be much longer, and you can see very much fainter stars and galaxies. But the other thing that you then become sensitive to is everything that's changing. You can so we're used to thinking of the skies, the heavens, as being static, as changing on timescales much longer than any human lifetime. But that is the story is far more interesting than that. First of all, there are things that move. Stars can be seen to be moving across the sky very slowly, but if you measure carefully enough over a long period of time, you can measure that. You can measure asteroids within our own solar system, and the Rubin Observatory will discover. I don't remember the number, but millions of asteroids over its lifetime, and
That's important. If dinosaurs had technology,
well, this is an interesting question. I mean, one of the scientific motivations is to ask the question: is there an asteroid with our name on it, one that's going to collide with the Earth? And the way you find it out is by cataloging as many asteroids as you can find and figuring out their orbits and asking the question whether anyone has any of them is likely to collide with us. So that is certainly one of the things. Yeah, go
So
ahead.
when you take, yeah. So when you take these pictures, Michael, so there are
Yes,
different
that's right.
filters that you're using.
So yes, by
Yeah. Okay.
combining the different filters, you basically can make a color picture. And there are 6 filters ranging over. This is a visible light telescope, so one ranges from the bluest, shortest wavelengths light that the Earth's atmosphere transmits, below which the ozone layer cuts you off, and goes to the longest wavelengths that the kind of detectors that we're using use. If you, it's what astronomers call the optical range, beyond which the technology for the detectors would have to change. So we will take images in those 6 different filters, and with that you can not just make pretty color pictures, of course, which we will do, but also measure very precisely the relative brightness in the different filters. Tells you about the physical nature of the objects that we're looking at, the stars, the galaxies, the asteroids, and everything else.
So are you moving
Oh,
the
absolutely. Yeah,
telescope
the
every
telescope
time you make an
is just bouncing
observation?
around the
Or
sky.
okay.
And indeed, one of the things that the telescope has been designed to do is move very quickly for exactly that reason. You don't want to spend all your time slewing. That's the jargon that we use from one region of the sky to another. You like to spend as much time actually taking exposures and as little as time as going in transition from one to the other, because that's sort of wasted time, as it were. So telescope, yeah, go ahead.
And make it, yeah, go ahead. No, I was just going to, so mechanistically, it's all robotics, right? So it is basically, if you turn it on, it will do its job and get the
Well,
data,
so you have to,
or
of course, program that robot rather carefully. So indeed, there's a great deal of discussion, which
right.
is about sort of two levels of questions. One is the one that you hinted at. You know, the sun has just gone down. Let's open up the telescope and start exposing. And you definitely have programmed in, here's the program for tonight. We're going to observe this field and then going to slew over to this field and this one, and it's 30 seconds a pop is the standard operations that we're planning to do. And so yes, there's an algorithm that says, okay, let's try to cover the sky this way through the night. There's a broader and interesting conversation about, okay, you have 6 different filters. For every exposure, you have to decide which one. You have this idea in the back of your mind that you want to see things change, but you also have this idea that you'd really like to measure the sky with as much sensitivity as possible. And the asteroids are moving quickly and the stars are moving slowly, and maybe a supernova will explode and you'd like to be sensitive to that. How do you design your survey to maximize your ability to do all that science? We went through an exercise now over 10 years ago where we tried to tabulate, or we basically wrote a book listing all the science that could be done. And basically every paragraph of this book was a PhD thesis or potential PhD thesis, and the book was 600 pages long. And that was 10 years ago. If we were to do it again, it would probably end up being twice as long. So there's a huge range of different science that can be done. I mentioned the asteroids, the large-scale structure of the universe that we had talked about before, the most distant galaxies and quasars, and everything in between. And we find ourselves wanting to do the science. We wanted to have it all. Again, we're astronomers tend to be very greedy and say, and so much discussion of, well, if we optimize the survey to make this science particularly powerful, is that going to be at the expense of our asteroid science or something else like that? And so coming up with that balance is a subject of much discussion that we're having a lot of fun sort of talking through now. Absolutely.
It's an
It's a classical
optimization
optimization problem.
problem. But
That's right.
one issue with
Yeah,
let me make a statement. You can correct me. One issue with being prescriptive, though, is that we are bringing
of
set
course.
of status quo biases to what to
That
look
is
for and
right.
where to
So,
look at, right?
astronomers are
Yeah.
used to this challenge. A colleague of mine has a mug that says something like in conscious expectation of the unexpected, or something like that. And so, part of the spirit of this is that well, first of all, we're going to allow ourselves flexibility to change our mind about how we carry out the observations if we see compelling reasons to do so. But what astronomers do is they take these series of pictures, and we keep everything. You may contrast that with particle physicists who have enormous accelerators where they bang protons together, and it turns out that there's so much information that comes out of those collisions, they have no choice but to throw away 99.99, I don't know how many nines go in there, % of the data because they simply cannot possibly keep up with processing it. So they have built into the hardware filters to just look for the things that they're looking for. And so when an astronomer hears that, they shudder because they know we are so ignorant about what's out there in the universe that we don't want to throw out anything a priori and sort of keep everything going keep every bit of data that we can.
Yeah. So these numbers are quite striking. So it says that, I don't know if I got this right, 32 trillion observations.
That's right.
Of
and
20
about
similar
numbers of stars. That's right.
And the
That's
similar
about
number
right.
of stars. Yeah. So we're talking about something like, is it 20 gigabytes
20 terabytes. You're off by a factor of 1,000. 20 terabytes.
20
yes.
terabytes.
Yeah.
20 terabytes.
At least the first incarnation of the Sloan Digital Sky Survey was a few tens of terabytes. LSST will basically get that quantity of data every night in the Rubin Observatory. So yes, and the end of the survey, you keep that up for 10 years, it adds up pretty quickly. And at the end of the survey, the numbers are tens of petabytes, close to 100 petabytes. And so, yeah.
Is it coming back to the US?
Yes. So as we just said, the telescopes in the Chilean Andes, but yes, will be piped in real time through a network that goes through first Brazil and then into Florida and then into the United States. And so yes, the majority of the processing will actually happen physically in the United States. That's right.
Okay. And so what do you hope to find here, Michael? So, assuming that the experiment goes well, you get tons of data. What are the specific areas that you believe will
one of the questions is the one that we were talking about before, namely this dark matter and dark energy question. Certainly one of the key themes that the Rubin Observatory is really designed to address. And one of the ways it does that is to, we talk about dark matter, and one of the problems with dark matter is by definition, by its very name, it is not something that we can see directly. And so you say, how can we learn about dark matter by taking pictures? Well, it turns out, as Einstein showed, that matter can bend light. So if you have dark matter, clumpy dark matter, because dark matter gravitates and pulls together gravitationally, it will imagine a clump of dark matter in a galaxy beyond that clump somewhere. The light from that galaxy will get bent and therefore distorted by that lump of dark matter. And this is an effect that's measurable. The shapes of galaxies are systematically distorted by the distribution of dark matter that's out there, and we can measure that statistically. And the current surveys are now just starting to begin to do this, and Rubin Observatory is really designed to do this on the large scale with exquisite precision. So this will give us a map now, not just where the galaxies were, which is kind of what we were talking about earlier, but where the dark matter is and how the dark matter is distributed. And that then gives you additional constraints on what the physical nature of the dark matter is. It turns out the dark energy also turns out to be important in all of this, and it all becomes very, very exciting that way.
So is it because so we can get some idea of the movement?
In the context of the dark, basically what we remember, I was talking before about trying to put together a coherent picture of how the structure in the universe today is related to what you see in the cosmic microwave background. what this will allow us to do is what we see. What we did with this Lone Digital Sky Survey is look at the distribution of galaxies. But I just said that galaxies represent most of the massive galaxies is in dark matter, and you really want to know what the dark matter is doing. The galaxies are almost an afterthought, and it's the afterthought that we can see, which is what we've used. But by measuring the distribution of dark matter, we can sort of measure more directly the quantity, the thing that at least in terms of the formation of structure in the universe, the thing that sort of counts more. And so this, and we can do this as a function of cosmic time, because again, we can look at different distances in the universe, and that's referring to different times in cosmic history. So we can ask the question, how did the dark matter clump together as a function of time? And that has the potential to give us fundamental new insights.
And so we're getting an idea of the distribution.
Yes, exactly. Gravitational lensing.
What
I'm not sure I actually used that term when I was describing this bending of light. But yes, this is gravitational lensing, which again is an effect first predicted by Einstein. It's an outcome of his general theory of relativity. I guess first seen famously for the change in the position of stars during a solar eclipse. But then seen in the context of galaxies only first seen in the late 1970s, and has become a growth industry in our field ever since.
And the other objective, as you mentioned, is sort of getting an inventory of the solar system. There is Planet 9 that is potentially out there as well, right?
People are excited about whether there might be another significantly massive planet-like object, I have to use my terms carefully, in the outer solar system beyond the orbit of Pluto. As you know, Pluto itself is the least massive of all, less massive than any of the planets that we usually refer to, and indeed there are several other objects seen in the outer solar system with comparable masses. But there's indirect evidence, which I am 80% convinced by at this point, that there's a significally more massive object quite a bit further away. This is the Planet 9 that you're referring to, and which made all the headlines. Right. We haven't actually found it yet. There's this quite indirect evidence that it might exist out there. Could Rubin Observatory find it? Perhaps. Others are looking. It turns out knowing the sky is a big place, and knowing where to look is not easy. And if it happens to be a place in its orbit that is incredibly sufficiently far away, it will be below the sensitivity of even the Rubin Observatory. So there's no guarantee of a success whatsoever, but it would be a truly exciting discovery.
There was some speculation, Michael. I don't know if this is just speculation.
Yes, I saw that. That was black hole. Yeah, that was a speculation. I think is a fine word for that. I mean, sure, why not? Let's call it a black hole. I'm not sure I have much more intelligent to say on that idea than that.
Okay, but this is a good segue into quasars, and this is another area of great interest for you. So I remember seeing some pictures in the 80s that this big jets that come out of these things. I remember, maybe I can't quite remember, but they used to be called quasars, and then they used to be called
quasars.
QSOs.
Is the term I use.
Are we back to quasars again?
People use those two terms interchangeably. The history is QSO stands for quasi-stellar object, which is referring to the fact that when they were first discovered, people remarked that if you just take a picture of them, it just looks like a dot, just like a star does in an astronomical image, and yet it wasn't a star. So thus quasi-stellar objects. That's really and then it got shortened to quasars, and that's the term that I like.
Yeah.
Yes, I think so.
It's easier. It's easier to say as well.
So our current understanding is that let's back up just a little bit. The Nobel Prize announced 2 weeks ago in physics was given to Andrea Ghez and Reinhard Genzel for their observations of stars in the vicinity of the very center of our own Milky Way, proving beyond any doubt that that there is a what we call a supermassive black hole, 4 million times more massive than the sun, at the center of the Milky Way, and so that our own Milky Way galaxy is not unique. In fact, as far as we can tell, galaxies, essentially all galaxies, all massive galaxies, sufficiently large galaxies, have a supermassive black hole in their center. So many questions then come up and say, well, where did that come from? How does it get there? How did it get started? And the next question you want to ask is, okay, if there's a supermassive black hole there, what happens when something wanders too close to it? So black holes, famously, once you cross the event horizon, you're never escaping again. So black holes, in practice, can only grow in mass. So a quasar is a supermassive black hole in the center of a galaxy into which material is actively falling. Once it falls all the way in, it's gone, and we don't see any. There's nothing further to see. But on the way in, it's not going to go straight in on a radially straight in. It's more likely to end up in orbit around that black hole. And if we're talking about gas moving in under the extreme gravity of the black hole, that gas is going to be moving enormously fast, and friction, viscosity in what's called an accretion disk that forms around a black hole causes it to heat up and glow. So paradoxically, a black hole, which is by definition sort of, well, that's the ultimate dark matter. There's nothing to see, but in its vicinity, things can grow astonishingly brightly. And indeed, that is our current understanding of what the quasar phenomenon is.
So I used to think that quasars are sort of long time ago. So you have to look back in time, billions of
the
years
black
to
holes,
see them.
the
true.
other thing to say is that when we're seeing a quasar, as I said, it's the process of material falling into the black hole. So we're watching the black hole grow, which is to say this is probably the mechanism by which the supermassive black hole in our own Milky Way grew. So our own Milky Way was probably a quasar sometime in the past. Most galaxies today have what are called quiescent black holes. That is, the material is not actively falling into them right now, and they're sort of just sitting there, and one has to work a little harder to infer their presence. But you're right. The majority of the quasars, the time in the universe when most black holes gain most of their mass and were shining as quasars was indeed in the what's sometimes called cosmic noon, when the universe was probably 2 to 3 to 4 billion years old compared to the 14 billion years old. And so, yes, quasars in the nearby universe, the recent universe, are quite rare, but they're quite a bit more common when we look at high redshifts.
And so if I understand this correctly, Michael, so we know that there are supermassive black holes in most of the reasonably sized galaxy centers, but we don't see this jets.
Well,
which is sort of a differentiating aspect.
Some of them, some of the nearby black holes do have jets, but you're right. In order to get the jets, you need the material falling in.
Okay.
Yeah.
You need the material. So any supermassive black hole, if that appreciable amount of material falls into it, it will
so there's
create a
two
jet
different
that is
related things that we've just talked about. One is as the material falls in, it goes in orbit around the black hole and forms what's called an accretion disk. So the mental picture you want to have is this black ball that represents the black hole itself, and a sort of a dinner plate around it, or a frisbee. I'm trying to draw a mental image here, which is the accretion disk. The jets that then come out are due to strong magnetic fields that thread that frisbee or accretion disk that I've talked about, and that comes out sort of perpendicular to your frisbee there. And whether that happens in every case or not is unclear. In fact, many quasars are shining very brightly and don't have any obvious sign of jets. So it's not a universal connection, and probably quasars go through different phases and different parts of their life cycle, if I can use that term, when they might have jets and other times they may not. And those are some of the fundamental questions we find ourselves at the forefront of research.
Yeah, I remember, like I mentioned, I remember seeing these pictures, and I was enamored by these jets that are
tens of millions of light
years
long.
Yeah,
hundreds of millions. That's really big.
Tens of millions. Yeah.
They can. Yeah.
But even tens of millions of light years,
it's quite
a physical phenomenon
indeed.
that you can actually observe is just incredible. Yeah. So in conclusion, I want to return to Rubin again. So you've been intimately involved with this. This is going to be operational
2 or 3 years. Again, COVID has slowed things down, like so many things in our lives. The official date has been October 2022 to start a 10-year survey of this project of mapping the heavens, and that will probably be delayed by some amount, and there's much discussion about exactly how to do that. But yes.
So if you look forward 10 years, Michael, what do you think? Let me ask it differently. What would you be most
one of the wonderful
about
things about astronomy is how bad we are at answering that question, which is to say we've constantly been surprised. If you can go through the mental exercise of going back 10 years or 20 years and asking yourself versions of that question, and in each case you would be wildly wrong about what the most exciting things to happen are. Astronomy really is a field in which our imaginations have been rather poor in guessing sort of what the most exciting things might be. So, if you ask had we done this 10 years ago, we would have only a handful of people would have imagined that we'd be finding colliding black holes with LIGO through gravitational waves, for example, and that is just one of the most exciting developments. Go back 30 years ago, no one was really talking seriously about black holes in the centers of galaxies, or the fact that planets exist around other stars, or that the universe expansion is accelerating. Just to talk about some of the most exciting things that have happened sort of in my astronomical lifetime. So I could tell some story about dark energy and dark matter, but I suspect 10 years from now we'll look back and say, boy, were we naive back there. We had just completely missed the point, or this discovery came out of left field and has really rocked the foundations. And again, it's up to our imagination to come up with what that might be.
Yeah. I was thinking on a very practical basis, if we find an asteroid heading for the Earth, and we figure out something,
that would be very good.
That would be out of the way. That could be useful. Excellent. Yeah. This has been great, Michael. Thanks so much for spending time with me.
Okay. Bye.
Thank you. Bye.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.